We've now seen the right triangle part of trig. We've seen now the graphical part of trig. Now we're going to try to put both of those together and start to work on the algebra side of trig. Vital skills for any time you're going to have an equation that has trig functions in it, and just vital skills for students going on into calculus. Before we get into this, I want to kind of take us back to some algebra principles here. Here I have written an equation. 3x minus 4 equals 8. Okay? And I want to talk about when is this true. Okay? So I'm going to start with some values of x. All right? And see what happens here. So let's see. Let x equal 2. All right? Let x equal 2. Well, what happens here when we let x equals 2? We get 3 times 2 minus 4 equals 8. Which gives us 6 minus 4, which is 2, is equal to 8, okay, which is not true. It's not a true statement, right? So that's false. Okay, now let's let x equal 4. When we let x equals 4, we get 3 times 4 minus 4 equals 8, which gives us 12 minus 4, 8 equals 8, okay? So now we get something that's true. And what we have done is found the value of x in this case, the only value of x, that makes this equation a true statement. This equation is not always true for every value of x. There's only one. Some equations have multiple values of x to make them true. But this one only has one. Now let's contrast this with this equation right here. X minus 1 squared minus quantity x plus 1 squared equals negative 4x. And let's just play with some values of x again. Let's let x equal 0. Okay, if x equals 0, we're going to get negative 1 squared, which is 1, minus 1 squared, which is 1, is equal to negative 4 times 0, which is 0. This is a true statement. Let's let x equal 2. We're going to get 1 squared, which is 1, minus 3 squared, 9, is equal to negative 8. Negative 8 is equal to negative 8. And once again, we get a true statement. And so if we keep playing around, we're going to keep getting true statements, and we might be led to believe that these two sides, these two expressions, are indeed equal, making the equation true for all values of x. Okay, and we can show that by simplifying the left-hand side here. Let's expand. X squared minus 2x plus 1 minus the quantity x squared plus 2x plus 1. And if we distribute some negative signs, we get x squared minus 2x plus 1 minus x squared minus 2x minus 1. And a bunch of things start to cancel out here. And we're left with negative 4x on the left side, which is obviously the same as the right side. Okay? And so this equation is true regardless of what we plug in for x. For all real numbers x, this is a true statement. When that's the case, your equation is called something special. Okay? It's called an identity. Which kind of makes sense as far as terms go, because identity in the traditional, English sense of the word is a name or something that describes who you are. So when you're saying I am blah blah blah, you're saying something. Hopefully that's something that's true. So an identity is an equation that's true regardless of the value of the variable. Okay, very different situation than up here, where we just have an equation that might be true depending on what value of x we have. In trig, we want to understand what the identities are, why we want to use them, and where they come from. When we're all said and done, there's going to be a list of at least 30 identities that we have to use from time to time. It's not going to be good to memorize a list, but if we understand where they come from, it's not as cumbersome to remember. Okay, so we work with trigonometry so much that it becomes convenient to replace trig expressions with equivalent trig expressions. Let's start with some we already know. Okay, when we defined sine and cosine in the first stage of our learning here, we had a right triangle. We had an acute angle, theta, and we just labeled some sides with respect to theta. We had the adjacent side, we had the opposite side, and we had the hypotenuse. And we said that the sine of theta was going to be defined as the opposite side divided by the hypotenuse. Okay. Now, if we were looking at this angle here, okay, then for that angle, let's label it alpha for now, okay? The sine of alpha is in this diagram, okay, is equal to the adjacent side divided by the hypotenuse. And if we go back to theta, that adjacent divided by the hypotenuse we define to be the cosine of theta. And so the connection between these two expressions here, I kind of gives rise to the word cosine, okay, which I think, if we look back in history, originally stood for complementary sine. Okay, meaning what? Meaning the sine of the complementary angle is the same as the cosine of your angle. Okay, the cosine of theta in this diagram is the same as the complementary sine, the sine of the complementary angle to theta, which gives us this little idea right here. The sine of theta is the same as the cosine of the angle that's complementary to theta. Okay, and in radians we say pi over 2 minus theta. And that works not only for the acute angles that we would see in a right triangle, but it works for all angles. And so it's an identity we can use whenever we like. And this idea works for all of the complementary functions. Okay, so if I wrote the tangent of theta, that's the same as what? Well, the complementary tangent, right, of the angle that's complementary to theta. Same thing for secant of theta. The secant of theta would be the same thing as the cosecant of the angle that's complementary to theta. And you can reverse all these as well. So, for example, the cosine of theta is the same as the sine of the complement to theta, which we write as pi over 2 minus theta. Okay, so you can fill in the other two that go with that. Those just make sense from right triangles and complements to angles, but they work for all angles. An angle in quadrant 3, for example, for sine, which is negative, would throw you back to quadrant 2 for the cosine, so it makes sense for non-acute angles as well. Now, a lot of our identities are going to come from the unit circle, okay, at least to make them obvious, I think. So let me go ahead and draw in an angle here. It'll be an acute angle, but it doesn't have to be an acute angle. But a lot of these things are going to, I think, make real perfect sense when we kind of look at how we've started to define trigonometry. Okay, so here's an angle theta, and here's a point on the unit circle, okay, x comma y. This is a unit circle, so that distance is 1. Okay, and if I extend a perpendicular down to the x-axis, then we have x comma y, and remember, this could be in any quadrant, not just quadrant 1. Okay, we've already kind of touched on these, but remember, if we talk about the unit circle, we define the cosine of theta to be the x-coordinate on the unit circle, and we define the sine of theta to be the y-coordinate on the unit circle, which means that we had the secant of theta to be 1 divided by the x-coordinate on the unit circle, cosecant of theta to be 1 over the y-coordinate on the unit circle, the tangent of theta to be the y-coordinate divided by the x-coordinate on the unit circle, and the cotangent of theta to be the x-coordinate divided by the y-coordinate. Okay? Now, if we do some simple substitutions here, we can come up with a bunch of identities that we call reciprocal identities, okay, which we may have already understood and encapsulated here. Okay, so for example, the secant of theta. When we graphed secant of theta, we used this principle already. Okay, but the secant of theta, that's 1 over the x-coordinate, correct? Well, the x-coordinate in the unit circle is the same as the cosine of theta. So we could write the secant of theta is the same as 1 over the cosine of theta. And if we find that fact useful, we can use it. And we have found it useful when graphing secant of theta, or secant of x. Similarly, you have the cosecant of theta is the same thing as 1 over the sine of theta. And I think, if you like, let's see here, the tangent of theta, right, is y over x, which if you flip it is 1 over x over y, and so these two guys are also reciprocals, tangent and cotangent. Okay, so just thinking in terms of the coordinates on the unit circle, we get those identities, so I don't think those are going to be difficult to remember, or at least come up with on our own if we forget. So we call those the reciprocal identities. We highlight those. Now, quotient identities, pretty straightforward as well. If you look at the tangent of theta, it says tangent of theta is equal to the y coordinate on the unit circle divided by the x coordinate on the unit circle. And if we do some replacements there, the y coordinate on the unit circle is the sine of theta. So I could replace y with sine theta, and similarly I could replace x with cosine theta. Okay, so it's going to be very convenient from time to time to convert a tangent of theta to a sine of theta over a cosine of theta. And similarly, you would get cotangent of theta would be the cosine of theta over the sine of theta. Okay, so there are many times where you want to convert tangents and cotangents in terms of sines and cosines, and that's how you do it, using a quotient identity. Okay, let me highlight those. And then my favorites here are the Pythagorean identities. Okay, if we look at this right triangle right here in quadrant 1, it doesn't have to be in quadrant 1, but just for visual purposes it is. And we use the Pythagorean theorem. It would say x squared plus y squared equals 1. So the x-coordinate in the unit circle squared plus the y-coordinate in the unit circle squared equals 1. And you say, well, yeah, no kidding, because that's the equation for a circle of radius 1 that's centered at the origin. Yes, that's good. But let's do some replacements here. Okay, what is the x-coordinate the same as? Well, it's been defined as the cosine of theta. Okay, so the cosine of theta squared plus the y-coordinate of theta squared, which is sine of theta. I think I said y-coordinate of theta. I didn't mean to say that. I meant the y-coordinate of the unit circle squared, but that's the sine of theta squared equals 1. So there's a Pythagorean identity, because it came from the Pythagorean theorem, that we'll use many, many times. Now, let me just talk about some notation real quick here. It is commonly written, instead of writing parentheses cosine theta parentheses squared, to write cosine, put an exponent right after the s and before the theta. Okay, it saves ink. And we're just going to understand that's what it means. Okay, the function cosine is being squared, not the angle theta. And it's the same thing as saying this up here, but it's much less to write. Okay, so you're going to see that notation used almost every time. And so that's how we'll write it. The cosine of theta squared plus the sine of theta squared equals 1. Okay, Pythagorean identity. And from that Pythagorean identity, we can do some things to come up with some more Pythagorean identities that are very useful. So let's see here. What can we do with cosine squared theta plus sine squared theta that's legal, which will lead us to some more identities here? Okay, well, I can do anything I want to both sides, except multiply by 0. So let's take both sides and divide them by cosine squared theta. And you're saying, why on earth would you want to do that? Okay, well, let's just see what happens when we do that here. Okay, now when I say divide both sides, that's going to amount to dividing each term, right? Because if I divide this whole side by something, I could split the fraction a plus b over c and make it a over c plus b over c. Okay, so the left side ends up looking like this. Divide both sides by cosine squared theta. and do the same thing on the right. There's no object over there except the 1. So that's simple to do. Now what do we get here? We're going to use some identities we've already talked about. Obviously, cosine squared theta divided by cosine squared theta is 1. Okay, so I've got 1. Now, what is sine divided by cosine? That's the same as tangent, right, over here. So this is really tangent squared theta. So 1 plus the tangent of theta squared is equal to, what's 1 over the cosine the same as? Because remember, 1 is really 1 squared. 1 over the cosine is secant of theta. Okay, so here you go. You have now another Pythagorean identity. Similar to the first, we used the first to get it, but I may have tangents and secants to work with instead of sines and cosines. So there I go. That's the second Pythagorean identity, and it came from doing something legal to both sides. And if we do the same thing except divide both sides by sine squared theta, okay, we'll end up with this. 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. Okay, those are the 3 Pythagorean identities. You'll see those a lot. Okay, and when you see things being squared, you're going to know, have bells and whistles go off in your head that you're probably going to end up using one of these 3 guys. Okay, and if we have time in class, to remind me to teach you some maybe mnemonic devices that help here. But I think if you just remember this one, then you can come up with those 2 real quick, because all you got to do is divide by the appropriate term. Okay, now we just finished our graphing unit, so we know what sines graph, cosines graph, and tangents graph look like in the parent form. And if you look here, sine, this is sine x, right? And this is tangent x. Both of these graphs are symmetric about the origin, meaning I can reflect any dot across both axes, and that that point is on the graph of sine x. Same thing for tangent. If we reflect across both axes, that dot is on the graph of tangent x. That means that these 2 functions are odd. Okay, odd functions. Now let's remind ourselves what an odd function is. It says that the function evaluated at the negative of the x-coordinate is the same as the negative of the function evaluated at the x-coordinate. Okay, opposite inputs give you opposite outputs. Okay, so what does that mean for us? It means if we have the sine of negative x, it's the same as saying negative sine of x. Okay, that does not mean I factored out the negative 1 from the inside and put it outside. That's not what it means. Okay, it's a property of odd functions. Similarly for tangent x, if you have the tangent of a negative x, that's the same as the negative of tangent x. Okay, odd even functions. Now over here, you have the cosine of x, and you can see that this graph is symmetric about the y-axis. That means cosine is an even function. Okay, even function. And even functions have this property, that opposite x values give you the same y value. So f of negative x is the same as f of x. So that tells us that the cosine of a negative angle is the same as the cosine of that angle made positive. Okay, odd even identities. Okay, so there are many more that we're going to get to, but for this lesson, those are the ones we'll use. What do we use identities for? Well, number 1, we use them for simplifying expressions. Okay, taking something that's complicated and making it look nicer. Okay, less terms, less symbols, less math to do. Okay, so let's take a look at this. Make this simpler. Okay, well, what would we do? Well, one thing, we have 2 fractions being added, so it's just kind of natural, I think, to get a common denominator and see what happens here. Okay, so to get a common denominator, we're going to take sine of theta over cosine theta. Now you're saying, hey, that's tangent of theta. I'm like, yeah, I know. And that's something you could do. You could make that tangent of theta, but then what would you do? So adding fractions is going to be something we do a lot with these identities and with doing proofs. So let's see what happens here. So we multiply by 1. That's going to help us get a common denominator for the first fraction. And the second fraction will do the same. So cosine theta over 1 plus sine theta. What do we need to multiply this by to get a common denominator? Cosine theta over cosine theta. Okay, so all I've done there is multiply the left fraction by 1, the right fraction by 1. All right, what happens? We know the denominator is going to be cosine theta times 1 plus sine theta. If you want to multiply it out, fine. It's going to be sometimes convenient, though, to leave it factored because things may cancel. Okay, so we'll see. Sine theta plus sine squared theta plus cosine squared theta. That's our new fraction. Okay, and hopefully you're saying already, hey, sine squared plus cosine squared theta, that's an identity. Okay, yeah, it is. That's equal to 1. Okay, that's equal to 1, and that's what you want to use it here for, is to make those two terms go away and replace them with the 1. So now you have in the numerator sine theta plus 1, right, over cosine theta times, and if I want, I can rewrite that as sine theta plus 1. Okay, so I have two terms that I can cancel out, okay, as an unnecessary 1. So this divided by this is 1, so still a 1 in the numerator. And that leaves us with 1 over cosine theta, which is secant of theta. And that's the simplest way you can write this original problem. So all this jazz, right, ends up being equal to secant theta, right? And you would not know that just looking at it. Okay, try this first problem for entrance ticket. Simplify this as much as possible. I'll tell you in the end, there's only one term. Okay, so that's what you're kind of aiming for. Okay, the second thing we like to do, mainly as a mathematical exercise, is to prove an identity. So they're telling us already that this stuff is equal to this. And our job is to prove it. Okay? Our job is to show that this is true. Okay? You've had these kind of exercises before, and one of the things that's commonly done that's wrong is to start messing with this like it's already in a true equation. Okay? So I'm going to go ahead and say this. You do not treat this as an equation. Your job is to take one side, mess with it until it looks like the other side. Or take the right side, mess with it until it looks like the left side. Or you can work with both sides as long as you don't do things to both sides, like multiply both sides by 2 or subtract 4 from both sides. Okay, so in this example, I'm not going to touch the left side. I'm just going to leave it alone. I'll work with the right side until it looks like this. Okay, so that's one strategy. All right, what do we do here? Well, I just can't help myself. I'm going to multiply through by cosine theta. Okay, that just makes sense to me. So cosine theta secant theta minus cosine squared theta. Okay, I'm just going to write an equal sign. I'm not going to do anything over there. All right, what is this? Well, cosine of theta times secant of theta. Secant of theta is 1 over cosine theta. Okay, so look at that. That's going to end up being 1, right? Still have the minus cosine squared theta. 1 minus cosine squared theta. Okay, now what? Let's go back. I have a cosine squared theta, right? So let's go back here and take a look. What is cosine squared theta? I have this identity here. So cosine squared theta would be equal to what? 1 minus sine squared theta. Okay, I just rearranged the Pythagorean identity that I already knew. Okay, let's copy this. Whoops. Let's copy that and take it with us back into this problem here. Edit, paste. Okay, so cosine squared theta I can replace with 1 minus sine squared theta if it's convenient for me. Okay, and maybe it will be here. So 1 minus, okay, parentheses, 1 minus sine squared theta. Okay, I'm replacing. That's equal to that, that's equal to that. Now, distribute the negative sign. We get 1 minus 1 plus sine squared theta. The 1's cancel, and look what I have. I have what I started with on the right side, now on the left side. Okay, so that is one way to prove this identity, but see, what I did was I only worked with the left. I did legal moves, substitutions and distributions here until I got what I had on the left, or on the right side. Okay, that's the idea behind proving identities. Let's do another example, and then I'll give you two to do for your entrance ticket here. Here I want to prove that 2 times the tangent of x times the secant of x is the same thing as this over here. Okay, you don't always have to work with the left. You can work with the right side. And that's what I'll do here, is I'll work with the right side until it looks like the left. Okay, let me unlock this because I want to bump this over here. I'm going to need some room, I think. And just so you know, it's generally a good practice to line up your equal signs as you go, and you do one thing per line. Okay, I don't want to see 5 equal signs in the same line string together. Okay, that's confusing to read. And you don't really know what you've been doing to the left side, the right side. It's hard to tell. Okay, so one thing per line, and go down the page, not across the page. Now I want you to see something here. Okay, 1 minus the sine of x. Okay, when you see 1 minus or 1 plus a trig function, bells and whistles, and this would be the same if it was trig function minus 1, trig function plus 1. Bells and whistles need to go off in your head, okay? And this is what I want you to see here, and you're going to do this a lot, okay? If I multiplied this by its conjugate, so to speak, okay, 1 plus the sine of x, then you're going to get 1 minus a trig function squared, okay? And when you have 1 minus a trig function squared, there's probably a Pythagorean identity you could use, okay? So I'm showing you this because it's not obvious maybe to you right now, but as you gain experience in these problems, you're going to see, oh, okay, that's what I need to do. I've seen it before. I can do it again here. And so I'm going to do the same thing here. I'm going to multiply top and bottom by the conjugate to 1 plus sine x. And in the next line, you'll see what gets created when you do this. Okay, what happens here? 1 plus the sine of x is the numerator. And the denominator, right, is 1 minus sine squared x. How do I know? Because it's the difference of squares factoring pattern, right? A minus b, a plus b gives me a squared minus b squared. Okay, let's do the second one, and then we'll talk about what to do with this. 1 minus the sine of x is in the numerator. The denominator is 1 minus sine squared x. So we have a common denominator, even though we didn't really mean to get one maybe. But what is 1 minus sine squared x? Okay, we use this already over here. Okay, so let me copy this again and bring it over, and you'll start to get the hang for what's what. 1 minus sine squared x is the same thing as cosine squared x. So I can replace these denominators here with cosine squared x. Simpler, less to write, okay, and may lead us somewhere as we go down. Cosine squared x. Okay, now what? Well, we got the same denominator, so let's combine these fractions and see what we get here. Cosine squared x, the numerator is going to be what? Remember, we had to distribute this negative sign. So it's 1 plus sine x minus 1. 1 plus sine x minus 1. Minus a minus, so it's a plus sine x. Okay, let me shrink some of this stuff down so we can proceed. Let's cut that. Draw group. Oops, I didn't get the whole cosine there. There. Draw group. Shrink it down. Boom. Move this up. Okay. What is this new numerator going to be? The ones cancel out. You get a sine x plus a sine x, so you get 2 sine x's in the numerator. And you've got cosine squared x in the denominator, which I'm going to rewrite as cos x, cos x. Okay. Now the other thing when you do identities is you want to kind of see where are you headed, right? Where are you headed? I want to try to get tangent and secant somehow in the numerator. I see I already have a 2. That's good. So how am I going to get tangent x and secant x? Well, look at the terms you got and see if you can group them conveniently or creatively here. Sine x over cosine x, there's the tangent you're looking for, right? And then if I write a times, if I write a times 1 in the numerator, okay, if I write a times 1 in the numerator, then the 1 over the cosine right there becomes the secant that you're looking for. And so I'm just about done. Let me just shrink down these last 2 lines and just write down my answer here. Draw group. There we go. Shrink that down a little bit. Okay, so just rewrite what you got here. How about the pen? There we go. Equals. All right, 2 tangent x times secant x. And now I'm done because I've made the right side look like the left side. Okay, so here are 2 for you to try. Prove that the cosine of u over 1 minus the sine u, ding, 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 equals secant of u plus tangent of u. And then prove 1 plus cosine of theta, ding, 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 over cosine theta equals tangent squared theta over secant theta minus 1, ding, 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 ding. Okay? There are many ways to prove these, so I'm not going to say that there's only one good way to do it. So see what you can do. And email me 2 questions you had in the lesson as well for your interest ticket, and we'll see you soon.